Good morning, students. Welcome to session 1 of linear transformations. So in the first chapter you have studied what's meant by vector space, example, subspaces, sum of subspaces, in some union and intersection of subspaces, and quotient spaces, results based on these, and also you have studied what's meant by homomorphism, isomorphism, and set of all homomorphism between the two any two vector spaces, the vector space and the field, and vector space onto itself. Okay, and also you have studied what's meant by annihilators. Okay, annihilators of a subspace, and we have studied many results related to annihilators, and you also studied the relations, the results related to inner product space. There we have studied one particular property, that is the homomorphism. What is a homomorphism? The homomorphism on a vector space from a vector space V into a vector space W is a mapping such that T of x plus y is T of x plus T of y, and T of alpha x is alpha times T of x. This holds for every xy belongs to V and alpha belongs to F, right? This is the mapping T from the vector space V into the vector space W is said to be a homomorphism if this condition holds true. So this homomorphism itself is called a linear transformation. T is here called the linear transformation from the vector space V into the vector space W. And also we have defined the linear transformations from V to the field F. Then such linear transformations are called as linear functionals, and we have studied many results related to this. Now in this chapter we are particularly interested in those linear transformations which maps from V, the vector space V, into the vector space V itself. Such transformations, linear transformations, are called linear operators. So in this chapter we are interested in studying the linear operator or the set of all homomorphisms from V unto itself, home of VV. So if V is of dimension n, then what about home of VV? You know that home of VV is of dimension n square, and we have proved that home of VV itself is a home of VW itself is a vector space, and its dimension is, if V and W are dimensions m and n respectively, then dimension of home of VW is m into n. That we have proved. Accordingly, dimension of home of VV is n square. Okay. Now, so combining these two statements, we can say that mapping T from V to V is said to be a linear if T of alpha x plus beta y is equal to alpha times T of x plus beta times T of y for every vectors x and y belongs to V. Alpha and beta are scalars. Here. Okay. Now, so you have studied another definition in your ring theory classes. Say an associative ring. An associative ring. Okay. An associative ring A. Ring itself is called the associative ring, right? Okay, because it is closed and it satisfies associative law with respect to multiplication only. That will be called an associative ring. Okay, an associative ring A is called an algebra. Okay, is called algebra over a field F. An associative ring A is called an algebra over a field F if A is an vector space A is an vector space over F, such that if A is a vector space over F such that for all AB belongs to A and alpha B belongs to field F, alpha times AB is equal to alpha A into B or A into alpha B. So an associative ring A is called an algebra. This is a very important definition. Is called an algebra over a field F if A is a vector space over F such that this condition holds true. So algebra is a ring as well as associative ring as well as a vector space, satisfying this additional property. Okay. Now we can easily show that set of all homomorphism from V to V itself is an algebra over a field F. Okay, set of all homomorphism from V to V is an algebra over F. So to prove it is an algebra over F, we need three binary operations. One is addition of vectors, multiplication of vectors, and the scalar multiplication. Say, how do you define any addition of any two elements? Say T1 and T2 are two homomorphism. Their addition is defined as T1 plus T2 of x is T1 of x plus T2 of x. This you know. And the scalar multiplication is alpha into T1 of x is alpha times T1 of x. Okay. And the addition multiplication is say T1 into T2 of x is equal to, okay, right, T1 of T2 of x for every x belongs to V, because both T1 and T2 are mapping from V to V only. Therefore, we can consider T1 into T2 of x as T1 of T2 of x or T2 of T1 of x. Okay. Generally, T1 of T2 of x is not same as T2 of T1 of x. Here, since the mapping is from V to V itself, so I can write T1 into T2 of x is T1 of T2 of x for every x belongs to V. So with respect to these operations, Hom of VV is an algebra over F. Okay. So now, therefore, since Hom of VV is an algebra over F, so this Hom of VV is denoted by the symbol A of V. Hom of VV is denoted by the symbol A of V. So why we are taken A means because this set forms an algebra, therefore it is denoted by A of V. A represents algebra, A of V. Therefore any element, any linear transformation belongs to Hom of VV means, so in future we will just take T belongs to A of V. It is understood that T is an homomorphism from V to V itself. Okay, T is an homomorphism from V to V itself if T belongs to A of V. Suppose we have a polynomial. Say you take some polynomial, say P of x. So that will be say A0 plus A1x and so on an x power of n, where these scalars are A's are belongs to F. Therefore consider a polynomial P of x over F means P of x belongs to where? P of x over F means P of x belongs to the polynomial field F of x. Suppose P of x is a polynomial over F. And suppose T is a transformation from V to V, or T belongs to A of V. Then what about P of T? P of T means it is a polynomial in T, say A0 plus A1 into T plus and so on an into T power of n. Means P of T is A0 plus A1t etc. an into T power of n. If P of T is 0, suppose P of T is 0. If P of T is 0, then we say T satisfies P of x, right? T satisfies P of x, or T is a root of P of x. So any value x0 such that P of x0 is 0 means what? x0 is a root of the polynomial P of x. Here P of T is 0 means we say T satisfies P of x or T is a root of P of x. Okay. So t may satisfy some other polynomial, say q of x also. T may satisfy some polynomial, say degree of q of x is say m, such that q of t is also 0. T may satisfy p of x as well as t may satisfy q of x also. So among such polynomials satisfied by t, we choose the smallest polynomial satisfied by t. Smallest polynomial, some smallest polynomial satisfied by t. Such polynomial is known as the minimal polynomial. This is very important definition. Minimal polynomial. Minimal polynomial. Okay, understand this? So minimal polynomial for a linear transformation t is the polynomial of smallest degree satisfied by t. Okay, minimal polynomial is the polynomial of smallest degree satisfied by t. Okay. So now, say look at this simple theorem. Suppose V is a vector space of dimension n over a field F. Then every t belongs to E of V satisfies some non-trivial polynomial in f of x of degree at most n square. If V is of dimension n, then t belongs to E of V satisfies a polynomial in f of x of degree at the most n square. Okay, so let us prove this. Suppose t belongs to A of V. Okay, now if t belongs to A of V, since A of V is a closed under multiplication, t into t square also belongs to A of V. Now t square belongs to A of V means t square into t cube also belongs to A of V, means all the powers of t definitely lies in A of V. Okay, t square, t cube and so on, every power of t lies in A of V. After certain stages, the elements may repeat. Okay, now suppose you consider the n square plus 1 elements in E of V. Consider n square plus 1 elements. I means t of 0, t square and so on, t power of n square in E of V. Now dimension of E of V is what? Dimension of hom of V is n square. Now we have n square plus 1 elements in E of V. Therefore these n square plus 1 elements in E of V must be linearly dependent. So they are linearly dependent means what will happen? Consequently, there exist scalars a0, a1, a2, etc. an square in F, not all of which are zeros, such that the linear combination a0 into I plus a1 into t plus a2 into t square and so on, an square into tn square is 0. Now an square into tn square is 0 means what? T is satisfying a polynomial of degree at most n square. So t is satisfying a polynomial of degree at most n square in f of x. This is the theorem. This is a very simple result. Okay. So now this theorem says that, so if t belongs to A of V, then say t satisfies a polynomial of degree at most n square. As I said, so it's a polynomial, it satisfies some polynomial means, so I can choose the polynomial of smallest degree satisfied by t. Such polynomial is known as the minimal polynomial, as I said, defined. Okay, now let's take up the other definition. Say now suppose t belongs to A of V, then this transformation t belongs to A of V is said to be invertible or regular or non-singular, one and same. Invertible or regular or non-singular if there exists an element s belongs to A of V such that s into t is I, identity transformation is same as t into s. S into t is equal to I, that's equal to t into s, then we say t is invertible. Okay, you know that when you say the element x has an inverse, x into y is equal to y into x is equal to 1. Okay, that's the general definition. So here the transformation t is said to be invertible or regular or non-singular if there exists an element, non-zero element, s belongs to A of V such that s into t that's equal to I, that's equal to t into s, because I have taken both the condition, because it may happen that s into t is may be equal to I but t into s may not be equal to I. I'll take such example. Okay, so here s is called the inverse of t, s is called the inverse of t, and we write s as T inverse. Okay, we write S as T inverse. And also an element in A of V which is not regular or which is not invertible is called singular. The element in A of V or the transformation in A of V which is not regular is called the singular transformation. Okay. So let us take up this example now. Say let us take, say let V be the real number space R3 over R or Euclidean space R3 over R, and you define a mapping T from V to V defined by T of X. X belongs to R3 means how X looks? It is a triplet X1, X2, X3 where each Xi's are real numbers. So T of X1, X2, X3 as 3 times of X1, X1 minus X2, 2X1 plus X2 plus X3. So I define T of X as like this. Then clearly as T is, we can show that this transformation T is regular or invertible. So if it is invertible, definitely inverse exists for this. That inverse is given by, say, S of y1, y2, y3 is y1 by 3, y1 by 3 minus y2, y3 minus y2 plus y1. Okay, this by simple computation we can find S of this type. So that we can observe that here S into T is I as well as T into S is also I, means identity transformation. Therefore, S is the inverse of T and T is invertible. Now let us take up the other example. Suppose V is the set of polynomials. Define two transformations, say S and T from V to V or belongs to A of V by S of any element of F of X. F of X means any element of F of X means they are the polynomials. Okay. Therefore, S of P of X you define to be derivative of d by dx of P of X. S is the differential operator and the other transformation T from V to V by T of P of X is T of definite integral 1 to X P of X d of X. P of X into dx. Now S is an differential operator, T is an integral operator. Here you can see that T into S is I, T into S is I, but S into T is not equal to I. Therefore, T is not regular, means T doesn't have a inverse. Okay, for if you want check this, say let us take the polynomial P of X is simple polynomial, say X square. Then what will happen? S of P of X means d by dx of P of X is 2x. Therefore, T of P of X is the integral operator. T of P of X is x cube by 3 integration x cube by 3 1 to x cube by 3 minus 1 by 3. Okay. Now look here. S into T of X square is S of T of X square. S of T of X square is what? X cube by 3 minus 1 by 3. Now S of x cube minus 1 x cube by 3 minus 1 by 3 means it is the differential operator. So this is 3x square by 3 minus 0. So it is x square. Now x square means S into T of X square is x square means what? This is nothing but I of x square. Therefore S into T is I. Therefore S into T is the identity transformation I. But you can verify that T into S will not be equal to I. Although S into T is I, but T into S is not I. Therefore, if you want to check whether the inverse exists for any transformation, you need to check both the conditions, like S, whether S into T is I as well as T into S is also I. Okay. Next, say we have a theorem. Look here. Suppose T belongs to A of V is invertible. Then this happens if and only if the constant term of the minimal polynomial for T is not 0. If T is invertible, if and only if the constant term of the minimal polynomial for T is not 0. Okay, you know that transformation T belongs to A of V definitely satisfies some polynomial. Okay, so let P of X be the minimal polynomial satisfied by T. So let P of X is equal to that I will take A0 plus A1x and so on an x power of n, where an is non-zero, n is not equal to 0 because it is so to assure that it is a polynomial of degree n. So we have taken an is not equal to 0 be the minimal polynomial for T over F. Okay, then by definition of a minimal polynomial, what will happen? P of t is 0. P of t is 0, right? Now first assume that the constant term of the minimal polynomial is not 0. What is the constant term? The constant term is a0. Suppose in the beginning you assume that the constant term a0 is not equal to 0. Now t satisfies p of x because p of x is the minimal polynomial for t. Therefore p of t is 0. P of d is 0 means what? According to this, a0 plus a1t etc. an t power of n is 0. But we have assumed that the constant term a0 is not equal to 0. This implies that a0 is equal to, you transform all the terms to the right hand side. This is negative of minus of the transformations. So this implies a0 into minus. So you take, since t is common among all these, you take t as a common factor. So this is minus of a1 plus a2t and so on an into t power of n minus 1 into t. Okay, so this implies 1 is equal to, because a0 is not equal to 0 means a0 in 1 by a0 exists. So if a0 is equal to 0, then 1 by a0 definitely not exists, right? So this is equal to minus 1 by a0 into a1 plus a2t and so on an t power of n minus 1 into t. Now you can see that, so this is like minus a1 by a0 plus minus a2 by a0 into t and so on, means it's a polynomial in t, means it's also according as a of is an algebra, the whole element, this itself is an element of a of v. So that element I will call it by s as minus 1 by a0 into a1 plus a2t, because this is again a transformation, because if t is a transformation, t square is also a transformation. Okay, yes, put s is equal to this, then s definitely belongs to a of v, and s into t is equal to what? Yes, this is s, this is t, s into t is equal to 1 means I, s into t is equal to y. Okay, put s is equal to this one, then s belongs to a of v and s into t is I. Similarly, we can show that t into s is I, because simply you take t into s is I means what you have to take. So you take common factor t in the beginning, that's all. Okay, t times t into minus a1 plus minus a2, sorry, minus a2 a2t and so on like that. So similarly you can show that t into s is equal to I. Therefore we have s into t is I, t into s is also I, means we can say t is a invertible linear transformation or a regular linear transformation. Okay, so we have assumed that the constant term a0 is not equal to 0. Okay, the constant term a0 not equal to 0, and we have shown that t is invertible. So conversely, you assume that t is invertible, and we need to show the constant term a0 is not equal to 0. Okay, if possible, suppose the constant term a0 is 0. Although t is invertible, you assume that yet a0 is 0. Then what will happen? Let's see. If a0 is 0, then p of t is 0, you know that, because p of x is a minimal polynomial for t. Therefore, p of t is equal to what? P of t is a1t, because a0 is 0. P of t is equal to a1 into t, a plus a2t square and so on, an into t power of n. This is equal to 0. This implies t common, take a common as t as common on the right. So this is a1 into I plus a2t and so on, an t power of n minus 1 into t is equal to 0. This implies, since t is invertible, t inverse exists, right? So you multiply t inverse on both sides of this expression, you get like this implies a1 into I plus and so on, an t power of n minus 1 into t already there, you multiply t inverse. T inverse is equal to 0 into t inverse, that's equal to 0. Okay, this implies what? a1 into I plus a2t and so on, an t power of n minus 1 is equal to 0, because t into t inverse is what? I, because t is invertible. So this implies what? T is satisfying a polynomial. T is satisfying a polynomial, say q of x, which is given by a1 plus a2 etc. an x power of n minus 1. T is satisfying a polynomial q of x of degree how much? n minus 1, which is certainly less than the degree of p of x. Is it possible? No, because we have assumed that p of x is the minimal polynomial, means that since the degree of p of x we have taken to be n is the smallest degree of a polynomial where t of x, where t satisfies. But we are arriving at a conclusion that t is satisfying a polynomial of degree less than that of p of x, which is a contradiction to the fact that p of x is the minimal polynomial. Why this contradiction arises? Due to our assumption that the constant term a0 is equal to 0. Therefore, a0 cannot be 0. a0 will not be equal to 0. Thus, t is invertible implies the constant term of the minimal polynomial a0 is not equal to 0. Okay. So, now say this result has two important corollaries, simple corollaries. So, this corollary says if V is a finite dimensional vector space over F and if T belongs to A of V is invertible, then T inverse is a polynomial in T over F. If V is a finite dimensional vector space over F and if T belongs to A of V is invertible, then T inverse is a polynomial in T over F. As I say, S is the inverse, S is a polynomial in T. Okay. Since proof is very simple, since T is invertible by the above theorem, what will happen? So, constant term a0 is not equal to 0. So, a0 plus a1t etc. an t power of n is equal to 0 with a0 not equal to 0. If a0 not equal to 0, then T inverse becomes what? As I said, we denote it by S. S is equal to what? Minus 1 by a0 into a1 plus a2t and so on an into t power of n minus 1. So, S or T inverse. This is certainly a polynomial in T. Therefore, if T is invertible, then its inverse is a polynomial in T over F. It's very simple. So, let us take up the next result. Corollary 2. Say if V is a finite dimensional vector space over F and if T belongs to A of V is singular, then there exists a transformation S non-zero, S not equal to 0 belongs to A of V, means S is a non-zero transformation such that S into T is 0 as well as T into S is also 0. So, look here, if T is a regular transformation, then S into T is I, T into S is I. If it is singular, then S into T is 0 as well as T into S is 0 for some transformation, for some non-zero transformation, yes. Okay. This may be taken as a definition for singular transformations also. So, we can say that the transformation T belongs to A of V is singular if there exists a non-zero transformation S such that T into S is 0, that is equal to S into T is equal to 0. Okay. So, let us prove this result. Say now, suppose T is not regular, means T is singular. T is singular means by the above theorem what will happen? The constant term of the minimal polynomial will be 0. If T is not 0 means its constant term must be 0. Now therefore, if P of x is the polynomial, minimal polynomial like a0 plus a1x and so on a n x power of n is a minimal polynomial, then according to this a0 is equal to 0. Therefore, what will happen? 0 is equal to P of t, that's equal to a1t plus a2t square and so on an t power of n. Now I will put S is equal to a1 plus a2t and so on an t power of n minus 1. Then S is definitely non-zero transformation. Definitely it is a non-zero because an is not equal to 0. Then S is not equal to 0 and S into t. S is this, t is what? Or this is equal to what? We can write this by say this is equal to a1 plus a2t and so on an into t power of n minus 1 into t, right? Can I write like this? So this I written by S, S into t is 0. Similarly, if I take t as a common in the beginning, it becomes t into S is 0. Therefore, S into t is 0 as well as t into S is 0. Okay. Now, the other theorem, this also can be taken as the definition for a singular transformation. So, this theorem says if T belongs to A of V is singular. If T belongs to A of V is singular, if and only if there exists an element V not equal to 0 belongs to V such that T of V is equal to 0, means a transformation T belongs to A of V singular if and only if there exists non-zero vector V belongs to V such that T of V is equal to 0, or the transformation T is singular if it transforms non-zero vector to 0 vector. V is a non-zero vector, T of V is a 0 vector. Therefore, a transformation T is singular if it transforms non-zero vector to 0 vector. But a regular linear transformation always transforms non-zero vector to non-zero vector. We have seen that if V is not equal to 0, then T of V is certainly not equal to 0. But for a singular transformation, although V is not 0, but T of V may be 0. Okay. So let us prove this. Suppose T belongs to A of V is singular. Then by the above corollary, what will happen? Then there exists some non-zero transformation S in A of V such that S into T is 0 as well as T into S is 0. Now S is not equal to 0 means what? For a non-zero transformation there exists at least one when you say some S is a non-zero transformation means it transforms at least one non-zero vector to non-zero vector. Okay. So since S is non-zero, there exists some vector, say W, belongs to V, okay, such that S of W is not 0. S of W is not 0. Okay. Now S is also a transformation from V to V, so S of W is not 0. Now S of W, where it lies? S of W also lies in V only, because S is also a mapping from V to V. Now S of W is non-zero, it's a vector. S of W is a vector. That vector I taken to be V. S of W is equal to V. Then certainly V belongs to V. V is not equal to 0 because S of W is not equal to 0, and T of V. T of V is equal to what? T of V means S of W. So this can be written as T of S of W. But T into S is what? 0. 0 of W, but 0 transformation of W is 0 for every W. Okay. So 0 of W is 0 for every W. So we have shown that if T belongs to A of V singular, then for a non-zero vector V belongs to V, T of V is 0. T of V is 0. So one part of the proof we have proved. Conversely, suppose there exists a non-zero vector V in V such that T of V is 0. What we have to prove? T is singular. If possible, suppose that T is not singular. If T is not singular means T is regular. T is regular means T inverse exists. T inverse exists, and so T of V is assumed to be 0 we have. So this and T of V is 0 implies what? You apply T inverse on both sides. This implies T inverse of T of V that's equal to T inverse of 0. T inverse of 0 is what? 0. Okay. This implies I. T inverse into T means what? I. Identity transformation of V is 0. I of V identity transformation, you know that it transforms every vector to itself. But I of V is 0 means what? V should be 0. V should be 0, which is a contradiction because we have assumed that V is a non-zero vector in V. So why this contradiction arises? Due to our assumption that T is not singular. Therefore, T must be singular. So that result says, so T is singular if and only if maps non-zero vector to 0 vector. Okay. This is also a theorem result which can be taken as a definition for singular linear transformation. So now let us take up another result. So suppose the transformation T belongs to A of V is invertible if and only if T maps V onto V. So invertible means the mapping must be onto. Already we have taken this definition in some proving many theorems, right? Now we are going to show the transformation T belongs to A of V is invertible if and only if T maps V onto V. V onto V. Okay. First suppose T belongs to A of V is invertible. Okay, we have to show T is a onto mapping. Then T is invertible means what? T inverse exists. Now T inverse exists. Okay. Now let V belongs to V. Let V belongs to V, which is in the image space. That's also V. Let V belongs to V. Then this V can be written as, can I write it as T of T inverse of V. Okay. Now V belongs to image space V. Then T inverse belongs to where? T inverse V belongs to the domain space V. So T is a mapping on the domain space of V. Therefore, V can be written as T of T inverse of V. Whence T of V is equal to V. Therefore, T of V is equal to V. Therefore, T is onto means, how to show ontoness of any linear transformation? We take, if T from V to W is onto, say for every Y belongs to W, there exists some X belongs to T such that T of X is equal to Y. That only we have proved. We have taken V to be an element here. Then T inverse V belongs to V here. T is a mapping from where to where? T is a mapping from V to V. Okay. We have taken V belongs to V here, and then T inverse V belongs to here. Then T apply on that, and that will gives the V itself. Okay. Therefore, T is onto. So we have assumed that T is invertible, and we have shown that T is onto. Conversely, say let us take T is onto. Conversely, let us take T is onto, and we show T is invertible. So suppose T is not invertible, then what will happen? Let's see. We are proving it by counter-positive method. Suppose T is not invertible, then T is not invertible means then T is not regular. T is not regular means T is singular. T is singular means what will happen? And so there exists a non-zero vector V1 belongs to V such that T of V1 is 0. Just now we have proved this result. So because singular transformation transforms non-zero vector to zero vector. Now let the dimension of V may be n. You assume that the dimension of V is n. Now V1 is a non-zero vector in V. So every non-zero vector is linearly independent. You know this. So this linearly independent vector, we can extend it to form a basis of V. This also we have proved in vector spaces. So this non-zero vector V1, I will using this V1, so I will extend I will extend it to a set. That set forms a basis for V. Say that extended set may be denoted by V1, V2, etc. Vn. How to construct this? You know that. So you take V2, which is not in the linear span of V1, and you adjoin V2. Then we will take V1, V2. So we will take some element, some vector which is not in the linear span of V1, V2. Then that element we adjoin like that. This is the maximum spanning set. Okay, maximum linearly independent set. Okay. Now let Y belongs to T of V. Let Y belongs to T of V. Then we have assumed that T is onto. If Y belongs to T of V means there exists some element X belongs to V such that T of X is equal to Y by definition of ontoness. Okay. Then as T is onto, there exists X belongs to V such that T of X is equal to Y. Now X belongs to V and V1, V2, etc. Vn is a basis for V means what? This X can be written as a linear combination of basis elements V1, V2, etc. Vn. Therefore, I written X as alpha 1 V1, alpha 2 V2, etc. alpha n Vn, where each alpha is belongs to field F. Now this implies if X is this, then Y is equal to T of X means T of alpha 1 V1, alpha 2 V2, etc. alpha n Vn. Since T is a linear transformation, this can be written as alpha 1 into T of V1, alpha 2 into T of V2, etc. alpha n into T of Vn. This is equal to alpha 1 into T of V1 is what? 0. We have assumed that T of V1 is 0. Therefore, alpha 1 into 0 plus alpha 2 into T of V2 and so on, alpha n into T of Vn. Alpha n into T of Vn is 0. That's equal to what? So this is alpha 1 into 0 means the remaining terms are alpha 2 V2, alpha 2 into T of V2 and so on, alpha n into T of Vn. Thus T of Y is an element of T of V, that Y being expressed as a linear combination of how many elements? Okay, n minus 1 elements. Therefore dimension of T of V is what? Maximum is, it is spanned by n minus 1 vectors means the dimension is less than or equal to n minus 1. less than or equal to n minus 1, but v is of dimension n. T of v is of dimension less than or equal to n minus 1 means T of v cannot be equal to v. T of v is not equal to v means what? V cannot be onto. Sorry, T cannot be onto. But we have assumed that T is onto, which is a contradiction. Why this contradiction arises? Due to our assumption that T is not invertible. Therefore, T must be invertible. Okay, understand this? So, we have assumed that T is onto and we have proven that T is invertible. Thus, T belongs to A of V is invertible if and only if T maps V onto V. V onto V. So, let us take the last result of this class. So, it also says, look here. So, this says the transformation T belongs to A of V is 1 to 1 if and only if T is onto, means in elements of A of V the transformation is 1 1 if and only if it is onto. This is a very important result because this result will be used in many important theorems. Okay. So, first let T from V to V be 1 to 1 and let dimension of V is n and let V1, V2 etc. Vn be a basis for V. Okay. Now, if V1, V2 etc. Vn is a basis for V, then you know that T of V1, T of V2 etc. T of Vn forms a basis of V, because it's a T of V1, if T is a mapping from V to W, you know this, if T is a mapping from V to W and if V1, V2 etc. Vn is a basis of V, then T of V1, T of V2 etc. T of Vn is a basis of W. But here W is V itself, therefore T of V1, T of V2 etc. T of Vn also forms a basis of V, because okay, so that we have shown it here, how T of V1, V2 etc. forms a basis of V. And now let V belongs to V be any element. Now let V belongs to V be any element. Then V can be written as, because T of V1, T of V2 etc. T of Vn is also a basis. So this V can be written as alpha 1 into T of V1 plus alpha 2 into T of V2 etc. alpha n into T of Vn. That means element of V can be written as a linear combination of basis elements. Since T is linear, this is equal to T of alpha 1 V1 plus alpha 2 V2 etc. alpha n Vn. That's equal to T of, now alpha 1 V1, alpha 2 V2 etc. alpha n Vn, it's a linear combination of basis elements of V. That vector I can taken to be V dash. So T of V dash is equal to V, where V dash is alpha 1 V1, alpha 2 V2 etc. alpha n Vn belongs to V, because it is a linear combination of basis elements. Therefore, for the element V belongs to the codomain space, then there exists an element V dash in the domain space. Both are V and V1, V itself. Okay. If V belongs to the codomain space V, then there exists an element V dash in the domain space V such that T of V dash is equal to V. T dash of V is equal to V. Therefore, by definition, T is onto. Okay. Now, we have assumed that T is 1 1 and we have shown that T is onto. Okay. Now, let us take T to be onto. Okay. Let us show T is 1 1. Say conversely, let T be onto. Conversely, let T be onto. We will show T is 1 to 1. Now, to show T is 1 to 1, we will show that kernel of T contains only 0 vector. Okay. For this, let V belongs to kernel of T be any element, means arbitrary element. Then what will happen? By definition of kernel of T, T of V is 0. This implies T of V means what? It's a linear combination of basis elements Vi's, that we written it in a summation notation as summation from I is equal to 1 to n alpha I Vi is equal to 0. This implies, since T is linear, so summation I is equal to 1 to n alpha I into T of Vi is equal to 0. Again, we know that T of V1, T of V2 etc. T of Vn are also basis elements, means they are linearly independent. So it's a linear combination of basis elements, means alpha into alpha 1 into T of V1 plus alpha 2 into T of V2 etc. alpha n into T of Vn is 0 means what? Each alpha is must be 0, because these are linearly independent. Now these are each alpha is 0 means what will happen? So V is summation alpha I Vi and each alpha is 0 means V must be 0. now V is taken to be arbitrary element in kernel of T, and that element we have shown it to be 0. Therefore, kernel of T is 0. If kernel of T is 0, then we can declare that T is 1 to 1. T is 1 1. Okay, understand this? So we have assumed that T is onto, and we have shown that T is 1 1. Thus, the transformation T belongs to A of V is 1 1 if and only if it is onto. Okay. So these are the few results for this class. So let us discuss the other results in the next class. Thank you.